Got a couple of cardiac arrests down here too,
the one perpendicular to the magnetic field lines. So in this case, the cosine term comes into play, and in fact it reduces the flux. Rotating coils in a magnetic field is the way the most electricity is being generated, in fact. So this is a very important aspect of Faraday's law of induction. There's one more way to change the flux. So let's say we have our coil here, but it's out of the magnetic field, which again points out of the screen. And now, by moving this coil into the field, partially or completely, that also changes the flux through the loop. And in this case, we would also see an induced current. Let's do this exercise where we have loops in different orientation in relative to a magnetic field, changing or constant. And we'll see what is the direction of the induced current, if any. So in A, we have an increasing current to the left in the conductor, and which means that according to the right-hand rule, there will be a magnetic field that is circular about the conductor. So on the top half, it's going into the screen, and here on the bottom, it's coming out of the screen. So we have a field like this that increases into the screen where the coil is. So according to Lenz's law, this loop wants to create a field that opposes that external field. So it will try to produce a field like this out from the screen, and according to the right-hand rule, the direction of the current is therefore counterclockwise. In B, the situation is a little bit different in terms that the current in the conductor is decreasing. So originally, according to the right-hand rule, there's a field like this and going into the screen over here. But now, as the current is decreasing, this field is fading away. And in this case, the loop wants to maintain that waning field. So in fact, it'll try to create a field of its own that is in the same direction as the diminishing field. So according to the right-hand rule, the direction of the current would be clockwise. In C, the current is constant, which also means that the magnetic field which is oriented in this way is also constant. So there is no change in the flux through the coil, so the induced current is zero. Part D is pretty much the same as the part A, so there is an increasing field, and in this case the other way around. So here the magnetic field is into the page, so the coil will want to produce a field counteracting that one. So the direction of the induced field would be this, out of the screen, which again means that the direction of the current, according to the right-hand rule, is counterclockwise. In exercise C, we have an example where the area of the loop is being changed. we have this bar that can be moved to the left or to the right, and in fact in this question the rod moves to the left, effectively decreasing the area of the current loop. So in what direction will the electrons flow? Okay, so let's first think about the direction of the magnetic field. So when the loop here is diminishing, or the size of the loop is diminishing, it also means that the amount of flux is diminishing. So the loop will try to maintain the flux by increasing the strength of the magnetic field. So it will try to induce a magnetic field in the same direction. And according to the right-hand rule, the current would then flow counterclockwise. But the question is, what is the direction of the electrons? So the direction of the electrons is always against the conventional current. So in that case, the flow of electrons would in fact be clockwise. What about the magnitude of the current? We'll use Faraday's law to calculate the magnitude of the electromotive force induced. So it's the time derivative of the electric flux. So we're not worried about the minus sign because we already figured out the direction of the current, and now we'll just calculate the magnitude. So the change in magnetic flux, or magnetic flux, can be described as magnetic field times the surface area. Well, the magnitude of the external field doesn't change, so it is constant, and then we have to evaluate the change in the area as a function of time. The change in the area is the product of the change of the dimensions of the loop. So the vertical dimension L doesn't change. So we are only changing the horizontal dimension, and which we can call dx. And the change in the horizontal dimension is simply the product of the velocity that we are moving and times some time increment, dt. So lv times dt. So we get b times l times v times dt divided by dt, and these two cancel, and we get simply b times l times v. What about the current then? So we just found out that there's an electromotive force of this magnitude induced in this loop. So we can imagine that as being a simple, small voltage source, because the units of electromotive force are volts, that is electric potential. So we have this battery here, imaginary battery, that produces a voltage E or epsilon, and that will drive the current in the direction that we just found out, in this case counterclockwise. So the magnitude of the current must be the voltage source, or the value of the potential, divided by the resistance of the loop. So this whole loop is a conductor that has some resistance. So epsilon we found was BLV, and then the resistance R. So the smaller the resistance, the higher the current would be in the loop.